Morning, sir.
Yeah, good morning. So, good morning to you all.
Sir,
Yeah,
sir, in the last lecture, the problem which we did,
yes.
in that the vibro float used was 100 HP vibro float.
Okay.
So we should use web hall in that, na?
Yes, we can use the web hall. Actually, in that sum, we did use a typical application.
Okay, sir. Because we
Uh,
used D-aplonia there, but D-aplonia was for 30 HP vibro float, na?
correct. So, you should use the web app,
Okay, sir.
web hall.
Okay, sir.
Okay.
Sir,
Yeah,
sir, and about the presentation, when will it be, sir?
we will schedule sometime in the next. We said na last date is 30th of this month. So
Okay, on
after
30th.
after 30th, any date we will fix.
Okay, sir.
Okay. So, is there any confusion or everything is clear with regard to the project? Okay. So, let me start the today's lecture. Until yesterday, we were talking about the ground improvement in cohesive coarse grain soil, that is sands. We did talk about the compaction, dynamic compaction, and fiber of rotation. We try to understand the fundamental mechanisms of how these ground improvement techniques could able to successfully improve the engineering properties of granular material, especially sands. Now it is not only the sand, so that we will be needing ground improvement. We also need ground improvement, especially in clay soils also. So in fact, as compared with granular material, cohesive materials are more complex and requires more and more attention. And they also need very pertinent ground improvement technique. So today, let us try to understand about another ground improvement technique, that is sand drains or PVD. Both are same. When it was developed as a sand drain, but nowadays no more sand columns are being used. Now the use of PVD, that is prefabricated vertical drains, is more prevalent. So let us try to initially talk about the sand drains, then later on PVD. So this is the conventional compaction. Suppose suppose if you look at, there is a ground. So this ground is predominantly of clay soil. What the characteristic of any clay soil is, it should undergo the consolidation process. However, the consolidation is a long-term process, so you cannot achieve anything in the short term. And moreover, it depended on the permeability with which the water is getting expelled out from the soil sample. Suppose if you look at this schematic, there is only one way of water permeating from the soil, that is only in the either upward direction or in the downward direction. So accordingly, so we have conducted 1D consolidation, or we did discuss about 1D consolidation, so during your undergraduation program. But we also did understand that in order to achieve the 50% or 90% consolidation, we require substantial amount of a time, maybe in years. So but we may not wait for until such time. So in order to accelerate the consolidation process, what is the best alternative that is available, and so that the long term time requirement can be shortened to even couple of months. So that is the basic requirement of sand drains technology. Now in between, before the evolution of the sand drain technology, so in order to accelerate the consolidation, the people used to impose some kind of a surcharge load, additional surcharge load, that is called as a preloading condition. So preloading. So because of this imposition additional load, that is surcharge load, uh, the little fast the water used to get dissipate little faster, so little faster, but still, so it used to take quite a lot of time for consolidation to occur. But the preloading is said to be a bit successful when there was no technology of the sand drains. Now this surcharge load is overcome by another technology that is called as a sand drain. Now the very basic is, why should we go for accelerated consolidation? So basically, if you look at any ground improvement technique, the ground improvement is required for a loose soil, loose sand, or if it is a clay, where it can undergo substantial amount of a settlement. So which is even behind the permissible settlement prescribed by various codes. So therefore, if that is the case, then how should we accelerate the settlement or the consolidation and thereby minimize the post-construction settlement? Now, the basic principle is that, let us try to imagine. Now, so this is the site. So site on which we want to build a structure. Now, as a result of superstructure, there is a possibility of the settlement inside the soil sample. Now suppose, what if I preload the same soil even before the construction of a superstructure and accelerate the consolidation and So that is why it is called as a 1D consolidation. While in this case, the water molecule can.
Sir, your slides are not visible.
Slides are not visible.
No, sir.
Okay, just a minute. Yeah, now.
No, sir. It's coming, I think. Yes, sir. Now it's visible. Sir, but previously what you
No.
explained was all blank because your voice was not coming, sir.
Oh,
Yeah, from this slide only your voice broke and it was not coming, sir.
acha. Then I have to explain everything.
Yes.
Okay.
So lastly, you were discussing what happens if preloading is done before the construction of superstructure.
Okay. So that means this slide.
Yes, sir.
Okay. Okay. Good. So let me explain. Now just imagine a situation where there is a ground. So there is a natural soil and you want to build a superstructure on that natural ground. Now as a result of the construction, you could envisage some kind of the settlement in the downward direction. Okay. So the settlement that you know how to calculate it. But just imagine when the settlement degree of settlement is exceeding the prescribed limit stipulated by codes, then what could be the alternative? So there is no alternative except going for the ground improvement. Now, so when you say ground improvement, what should we do? So what should we do is we should accelerate a phenomenon such that whatever the settlement that supposed to should occur the post construction of a structure should occur pre-construction. So by some means. So the means is called as a preloading condition. The means is called as the preloading mechanism or sand drain mechanism or compaction mechanism or stone column mechanism, whatever it is. So therefore, when you talk about any ground improvement technique, it is a mechanism that either accelerates the consolidation or improves any engineering properties of the soil. So just imagine you have a load versus time graph, load versus time graph. When you take a two stages, one is before construction of a superstructure on a ground. What we do is we mimic the same kind of the loading condition on the soil, but in the form of a free loading. In the form of a free loading. So therefore, so this is the initial condition where there was no load on the soil sample, but with time we increase the surcharge load. Now the consequence of increasing the preload is there is an increase in the settlement. So increase in the settlement. Therefore, from the origin, so above indicates the loading condition in the y direction, and the below indicates the settlement in the y direction. Now we can keep on. We should keep. We should never ever keep on increasing the preload on the soil sample, because so the excess preloading condition may shear the soil, the clay soil. So therefore, there should be some amount of the limit on the height of the preloading condition. So therefore, this is the height. So based on the bearing capacity or based on the design criterion, we should impose the height of the surcharge load. Then the same surcharge load is maintained for some time until such that so the ground undergoes the desired amount of the settlement or the maximum amount of settlement that it can able to go, and thereafter remove the free load. Now upon removal of the free load, since initially the soil is under tremendous stress, so there is some kind of a heave or a rebound. So this is the rebound. Now suppose if you look at the step below, here what we have done, we imposed the load and removed also, but there was no full rebound of the settlement. full rebound of the settlement. So this is the rebound, but the majority of the settlement is the permanent settlement. Permanent settlement. Therefore, there is no recovery of settlement of that particular soil sample. So that is an advantage. So because of the freeloading condition, so we did achieve a condition where the settlement has undergone permanent. Now, upon removal of the preload, then we started building our superstructure. Now, the load obviously should be lesser than the load that is applied during the preloading condition. So, during the preload, normally we apply more than the structural load. So, since we already applied excess amount of load even before the construction of the structure, the soil has undergone already the desired amount of the settlement. So, therefore, the post construction of any superstructure, you could envisage that the settlements are quite minimal. It could only compensate some amount of the rebound. That's it. So, this is the beauty of the preloading condition. So, what I mean to say is, the main purpose of any ground improvement technique is it should mimic the consolidation settlement that is going to happen the post construction of any structure, uh, even before the construction of the structure. So, this is the primary purpose. Now, let us try to understand the mechanism of a sand drain and what is the sand drain. So, basically, sand drain. So, sand drain means, so it is a column, a vertical column, as you can see in these pictures. So, this is a column constructed within the soil sample from the natural ground level to a particular millimeter or 300 400 millimeter depending upon the design requirement. It is a column, so built within the soil mass and filled with the sand material. So now we fill the sand. So upon filling of the sand, something that is happening is it drains out the water within the soil mass from the surrounding soil. So that's what is the meaning of sand drain. A material that is a sand which could able to drain out water from the in situ soil. So for vivid understanding, I have taken a realistic example where you can see, if you look at this diagram, so this is a surcharge load to be imposed in the future, and this indicates the 1D consolidation. Suppose if we superimpose this surcharge load, now this clay can undergo the consolidation, but only because of the 1D consolidation. So this is because the water can permeate either in the upward direction or in the downward direction, depending upon the kind of the permeable layer available either at the top or at the bottom or at both top and bottom. So this is typical 1D consolidation. Now here if you look at the path traveled by water molecule, that decides the consolidation time. So in case of 1D consolidation, the path traveled by water molecule is substantially high. So therefore, you need huge amount of a time for consolidation to occur and thereby accelerate the settlement. Now the fundamental principle of the sand drain technology is it first shortens the path traveled by the water molecule. Now when you shorten, so this shortening can be done in the only vertical direction or vertical as well as in the lateral direction. So that's what has been shown in this diagram. Now in order to shorten that one, what we have done is we have built a sand column. So this is the sand column. We have built so many number of sand columns. So at a particular interval. Now if you look at carefully, the sand has significantly high permeability as compared with the clay. Now this contrast in the permeability plays a vital role for accelerating the consolidation. Now because of this contrast in the permeability, all sand columns will act as some kind of atmospheric conditions, and there they will allow water to permeate into the sand columns. Now when there is a contrast in the permeability, the water obviously tries to move the nearest available atmospheric condition. So here that is available in the lateral direction, not in the vertical direction. But still the water has the choice to move in the vertical direction as well as in the lateral direction. So that's why it is called as a 3D consolidation. The water can move vertical as well as in the lateral direction. When I talk about the lateral, so in any lateral direction, in both the directions. So 1, 2, 3. So since the water can able to permeate in all the three directions, so it is called as a three-dimensional consolidation. Three-dimensional consolidation. So this is how we reduce the time required for a water molecule to travel to a particular distance. There is a reduction in the time. Obviously, there is a reduction in the consolidation time. So this is the fundamental principle of the sand drain. If anybody has any question, you are free to ask.
Sir,
Yeah.
the gravels have more permeability than sand.
Yes.
So why we haven't used gravels here? Why sand is being used?
No, you can also use the gravel.
Okay, sir.
Okay. If you use the
Yes.
sand, it is called as a sand drain. If you
Okay, sir.
use the gravel, then that is called as a stone column.
Okay, sir.
Okay, I will also explain when sand is required, when gravel is required.
Okay, sir.
Okay. So this is again the mechanism of the sand drain, as you can see. So these arrows indicate the movement of water. So upon imposition of the surcharge load after installation of the sand drains. So these are all sand drains. They collect the water, and all the water, so because of the surcharge load, they will come onto the surface, and from surface they will be channelized to a drain. Okay, so the consolidation means expulsion of the water. So therefore we are fulfilling the condition of the consolidation mechanism. And these are all the arrangements. So these are all the arrangements that will show how the consolidation can happen. So over a bigger area. So these are all the drains. These are the caps. These are connected to the drainage. So this is the network of a drainage. All the network of a drainage is again connected to the vacuum pump or the pump, so which collects all the water and discharges to the nearby drain. And this is how so the soil undergoes the accelerated consolidation process.
So this method will not work if surcharge is not there, na?
No, if there is no surcharge, no sand drain working.
Okay.
So nowadays there is another ground improvement technique that is becoming the more prevalent is the vacuum preloading. So in case of the vacuum preloading also, they insert or drive some vertical drains into the ground, but they don't fill these drains with anything. Okay, and all these drains are interconnected, and all are interconnected to one point, and where instead of the water, the vacuum is applied to squeeze out the water. So huge amount of vacuum is applied. In fact, one of you also presenting the vacuum preloading conditioner, the vacuum consolidation. So this is how it works. So first, on a selected clay soil, so at the designed interval of spacing, so all drains are installed up to the desired depth. So this is soft clay, and all drains are interconnected, and they are all connected to a particular point, and from there the vacuum is applied. Just imagine, so when we are applying the vacuum from so many number of points, and when you are collecting the water from so many number of points, so less time is required to consolidate the soft clay. So earlier when you talk about the sand drain, you are imposing the surcharge load to accelerate the consolidation by squeezing out the water. Now in case of the vacuum consolidation, instead of the surcharge load, we apply the vacuum pressure. So that's what is the difference between the sand drain and the vacuum preloading. So this is the method of the construction. We require some kind of the vibro flotation technique help to construct the sand drains, or we can also go for simple ordinary boring. So we can go for a placement of stone columns by vibro flotation technique. So this also distinguishes between the sand drain. So this is preload with the stone columns and vibro flotation and the dynamic compaction. So the dynamic compaction on the vibro flotation is, as I stated earlier, it is valid for the granular soil, while sand drain technology is valid for the cohesive soils. So this is another mechanism. This picture shows what happens when there is a large embankment. So we can see of the settlement underneath the surcharge load, but at the same time you can also observe some kind of the heave at the just outside periphery of the embankment. So therefore, when you try to implement this technology, you should be a little bit careful. So the heaving should not cause damage to the adjacent buildings. So that heaving depends on two things: how soft the soil is and how much the surcharge load that you are imposing. So these are the two things. So there is a wonderful case study. So this is one case study I come across. There are several case studies. Now, so here what happened is a designer has designed the ground improvement by the stone column. So this is at Wilmington Port Authority, Cuba. So you can see, so this is the sand drain. So this is the area. So that the engineer wished to improve by the sand drain technology. So he has designed everything. So his primary purpose is they want to construct a molasses storage tank on a 20-meter thick organic clay, and these are the properties of the clay. The initial wide ratio is 1.72. The vertical coefficient of permeability is this much, and coefficient of consolidation in the vertical direction and coefficient of consolidation in the horizontal direction. So one important thing is, when you talk about the sand drain technology, the water moving or permeating in both vertical direction as well as in the lateral direction. So therefore you should understand that the permeability is happening in vertical and lateral, or the vertical or in the lateral direction. So usually the permeability in the lateral direction is higher than the permeability in the vertical direction. So when there is a distinction in the permeability, so as the consolidation, that's why the coefficient of consolidation in the vertical direction is different than the coefficient of consolidation in the horizontal direction. So since the permeability is approximately 1 to 2 times higher than the vertical direction, so as the coefficient of consolidation. Now let us come to this case study. So here the engineer has given 1 year time period to accelerate the consolidation to 90% of degree of consolidation. So he did design. He found that sand drain of 300 millimeter is sufficient, triangular spacing, and target surcharge of 10-meter height. So 10-meter height. Now, one of the peculiar phenomenon that happened is, whatever he has anticipated some kind of the failures, so everything was correct. But one kind of a failure that he did not envisage is called as a deep-seated failure. This is called as a deep-seated failure. So this you have already heard. So when you have, I don't know, might have during your undergraduate program. So when you are talking about the design of retaining walls, so this is called as a deep-seated failure. Now what is so peculiar about deep-seated failure is that the failure plane, the starting of the failure plane might be in our boundary, but the ending or the exit of the failure plane may be in somebody's boundary. As you can see here, so this is the boundary between the two areas. This place belongs to one person and this place belongs to another person. So because of this sand drain technology and because of the imposition of 10 meters surcharge, a deep-seated failure has started developing, and the adjacent building fellow, he started observing failure or cracks in their floor. So this was the first observation. So this is because, so he did not anticipate the thrust in the lateral direction because of the vertical load. So because of this thrust, so there is an excess lateral pressure on the pile foundation, as you can see here on the pile foundation, where there are two things. First of all, this pile foundation was not designed for such lateral load. Second thing, the engineer who designed the sand column did not anticipate that there could be a possibility of the lateral earth pressure. So because of these two things, so there was a huge some kind of the litigation as went on. So this person has sued this person, so on and so forth. But the moral of the story is, when you try to design anything, so please try to envisage the phenomena which might not be designed originally. So do not never ever stick to only the bookish knowledge. Okay, so because the books always tell you until that point what the technology has been developed. They never talk about what will happen in the future. Okay, so because that's why the books you will see a lot of editions. So in each edition they will keep on augmenting the improvement in the knowledge. So this is one of the best case study. So now let us try to understand the fundamentals. So the principles of the freeloading. This is the consolidation graph, wide ratio versus the loading condition. So this is the consolidation graph. So when you are imposing the load, there is a decrease in the wide ratio. So initially there is initial wide ratio of E naught. Then after desired period amount of time, then the wide ratio has been decreased from E naught to E1. E naught to E1. Suppose if you try to understand everything in a curve form, you can see first what you call AB. So A to B. So this is typical consolidation curve. Typical consolidation curve. Normally this AB curve we will obtain in the laboratory. So when you do the 1D consolidation in the laboratory, we will get this kind of a graph. So we apply the load of sigma naught z, that is initial effective overburden pressure, then increase in overburden pressure, that is delta sigma. So because of delta sigma, there is a change in wide ratio, that is delta E. Then upon removal, that is construction of the permanent, rebound upon removal of the stress. So from the point B, suppose if you remove the load, you could see some kind of a rebound up to point C. So then at point C, then they started the construction of the building. So again there is a compression. So when there was a decrease in the wide ratio, so the same thing is reflected in the form of a shear strength also. As you can see, so this is a Mohr-Coulomb failure envelope, and this is the improvement in the shear strength. So because of the consolidation phenomenon. So when you do the freeloading or the sand drains, it is not only the acceleration of the consolidation, there is also improvement in shear strength of the soil. So this slide explains about two things, because there are two uh, technology that could talk about acceleration of the consolidation. One is the sand drain, next is vacuum preloading. So just for your understanding, I compiled this slide. As you can see here, there are three important points. When you apply the preload, it induces positive pore water pressure within the soil. But when you apply the vacuum, it induces negative pore water pressure. So this is the difference between preloading and vacuum. So preloading causes positive pore water pressure and vacuum causes negative pore water pressure. And preloading induces unequal vertical strain. So to understand the better, so this is unequal vertical strain. Suppose you have seen embankment. So if you look at this point and if you look at this point, the strain at this location is different than the strain at this location. So if you apply the freeloading condition, there is an unequal vertical and horizontal strain because of the difference in height of the surcharge. While when you apply the vacuum, so the vacuum can be applied uniformly. So therefore, there is a uniform stress on the soil sample. And the third important point is when you apply the free load, there is outward movement. That's just now I showed. Here also you can observe. Because of this free load, there is outward movement. There is outward movement in both the direction. But when you apply the vacuum, there is an inward movement. As you can see here, there is an inward movement. Inward movement. So these are the major distinctions between the preloading and the vacuum consolidation. And this graph talks about the various stress conditions that are going to develop on the soil sample. So this is the Mohr-Coulomb failure envelope. So this line is KF line. This is stress path. So this is stress path line and this is K0 line. K0 line means the initial condition exists in the ground as it is. This is the ground situation and this is stress path or the failure plane. Now what we have done? So we have taken condition A, where you can see the soil element is under two stresses. So we have taken an element from at a particular depth, not at the ground surface, at a particular depth. So there exists on the soil element vertical stress sigma 1 and the lateral stress K0 times of sigma 1. So here K0 means at rest condition because we did not impose any kind of a surcharge load. Therefore it is called K0 condition. Now from this state A, when we superimpose the surcharge load, that's what is called as a fill. You superimpose the surcharge load by filling. So when you fill, so from the initial condition, the state of the soil moves towards the failure condition. So that's what is represented by BC. AB. So here you are increasing delta sigma. And the same load is maintained for certain time. That is B to C, consolidation after fill placement. From A to B, we have filled or imposed the surcharge load. B to C, the same is kept constant for certain time. And then, so because of this one, there is a consolidation. So we achieve the C condition. Now, there are two things. This graph also talks about two things. From the K0 line, if you go above, that talks about, this talks about the fill condition, that is preloading. But when you talk about the vacuum freeloading or vacuum consolidation, so from A, where it is in situ field condition, we are not applying any surcharge load. Rather, we are applying the negative pressure. Negative pressure means it is inward. So in case of the positive pore water pressure, the thrust is in the outward direction. But in the vacuum, the thrust is in the inward direction. So therefore it is below. So the ground improvement occurs from A to E. Constant pressure is applied from A to E. So this slide distinguishes between the preloading and the vacuum consolidation in a very better way. There are some more details also about this one in the next slide. So you can see this is the failure envelope. A to B stress path due to freeloading. B to C consolidation during waiting period. A to E consolidation due to vacuum freeloading. So when sigma h is less than 0, no failure due to vacuum freeloading as stress path is moving away in horizontal direction. You can see when it is when you are filling, when the stress path is moving from A to B, if you further impose the filling, then it can reach the failure. It can reach the failure. But conversely, when you apply the vacuum, there is no possibility of the failure of soil at any point. So therefore, that is the beauty of the vacuum consolidation. No failure due to vacuum free loading, as the stress path is moving away in horizontal direction. It's not moving towards the failure plane, rather it is in horizontal direction, that too moving away. So preloading, so the horizontal strain is less than 0, outward horizontal movement, in vacuum free loading, it is inward horizontal movement because it is sucking the water. So stress path AD represents K0 condition, that is field condition. So this also explains the fundamental mechanism, differences in sand drain technology and 1D consolidation. So this graph is 1D consolidation. You can see, to achieve the 90% consolidation, hoping it requires above 40 years. But the same thing can be achieved in a couple of months when you go for the sand analysis. So 1D consolidation, 3D consolidation. How effective this talks about the effectiveness of sand drain technology. So this is the performance of the sand drain again. So when you talk about the sand drain, so we can talk about the variable diameter of the sand drain, variable spacing. So then this slide talks about the effect of the spacing and effect of the sand drain. So if you want to reduce the time required for consolidation, so initially, say for example, it took 1 year to consolidate, but if you want to further reduce, then what we can do is we can either increase the sand drain diameter or decrease the spacing. So within the same sand drain technology, by doing the parameter sensitivity, we can further reduce the time required for consolidation. So this slide also delineates the effectiveness or the fundamental principle of the freeloading and the vacuum. So when you talk about the freeloading, we always talk about change in the effective stress, that is the changes in the soil particles that is happening from the beginning till end of the consolidation. But when you talk about the vacuum freeloading, we always measure the change in consolidation in the form of a pore water pressure parameter, that is delta U. You can see the pore water pressure change, how it is changing with depth and with time. So this is initial condition and this is the final condition. So this is a typical cross section of the sand drain. So there is a surcharge load. So these are all the vertical drains, and these arrows indicate the path followed by water molecules. This is soft clay, and in order to monitor the settlement, we embed within the soil some kind of the piezometer. So this piezometer will measure normally the pore water pressure. So the pore water pressure can be related to the settlements or degree of consolidation later. So this part we can see, and there is a settlement plate, so by which we can monitor the settlement of the original ground. There is a drainage blanket. Which is laid on top of the ground, which interconnects all the sand drains. So this slide gives a lot of details about the complete arrangement, including the instrumentation required for the sand drains. We require the settlement plates for monitoring the settlements. We require piezometer to measure the change in pore water pressure with time. So this is soft soil. So these are some fundamental definitions. So just I will repeat. Sand drain is basically a hole drilled in a cohesive soil and filled with the sand. If it is filled with the sand, it is called as a sand drain. If it is filled with the gravel, it is called as a gravel column. Gravel column also called as a stone column. So we will talk about the stone column in the subsequent classes. then it is also called as a sand wick. But as I told, now sand drain is almost obsolete technology. Nowadays we use the PVD, prefabricated vertical drain. So that I will talk in the next class. So this is one of the most widely used technique for improving the engineering characteristics of soft clays. So main function is to accelerate the soil consolidation by shortening the drainage path as a result of activating the radial drainage. So this point I will clearly explain how to shorten the path and thereby accelerate the consolidation. So dissipates the excess pore water pressure, because when you are imposing the surcharge load, this causes generation of excess pore water pressure. But when you maintain the same surcharge load, the same excess pore water pressure gets dissipates with the time very fast due to the greater coefficient of soil permeability in the horizontal or in the radial direction. So increases the shear strength of the soil while reducing the post construction settlement. So this is the primary purpose of any sand drain technology. So when you apply the surcharge load, we can apply the surcharge load in two ways. One is free strain case, next is equal strain case. That means in case of the free strain case, the surcharge applied at the ground surface is flexible in nature, that is equal distribution. But this results in uneven settlement. Then opposite to this is equal strain case. So these are some applicability about the sand drain. The sand drain is applied when free loading fails to accelerate the consolidation. But free loading normally fails for a thick stratus. For a thick stratus, sand drain technology is very useful. So permeability of the clay is very slow, so that the time for pre-compression is very long. So this is the, because of this reason we go for the sand drain technology. Mostly employed for embankments constructed over a high compressible clay soils, based on consolidation theory of radial and vertical. So when you talk about the 1D consolidation, we did discuss about only drainage in vertical direction, but when you talk about the sand drains, both radial and the vertical drainage. So technique is effective in primary consolidation, not suitable for organic soils and peats in which compressions are dominated by secondary compression. So the primary compression means the expulsion of water from the voids. Secondary compression means is a compression due to the expulsion of water from the diffused double layer of the clay particles. So to remove the water from the diffused double layer, we require some additional forces like thermal or electrical. But when you talk about the surcharge load, it is the mechanical force. So therefore, the mechanical force is effective only to expel the water from pores, but not from the diffused double layer. So this is the reason the sand drain is valid only for the primary consolidation. So these are some typical geometry. Diameter normally varies from 150 to 500, but it can be more than 500 also. So created by filling sand into a hole in the ground. In order to make a hole, we can use any kind of driving technology, that is borehole technology, either by driving or jetting or rotary drilling. So spacing between two sand drains varies normally from 1.5 to 4.5. 4.5 is too high, so the common is on to 1.5 to 3, and depth we can go is up to 30 to 35 meter. So thickness of the sand blanket means it is the gravel blanket layer laid on the ground surface, which is covering almost all the sand drains. The sand blanket, which is 0.6 to 1 meter. Now this is the reason explaining why we should not go for the large diameter of the sand drains. Large diameter sand drains tend to behave as weak piles in soft soil. So this may have an effect of stress concentration on the drains. So if the diameter is too large, it may act as a load bearing column. When it is acting as a load bearing column, then that may redistribute the stresses, or it may affect the function of the drainage. So that is the reason we should not go for large diameter sand drains. So drain backfill material should have a sufficient permeability, and its particle size with no more than 3% by weight, passing CV number 200, that is 75 microns. Here backfill material means this sand. It should be pure sand. It should not contain any fine particles, not more than 3%. So This is the construction technology of a sand dry. These I will talk about these things maybe on Tuesday's class. I will stop it here.
Sir,
Yeah,
sir, once the consolidation is over,
yeah.
then is this sand taken out?
No, no, it will not be taken out.
Okay, sir.
It will be there forever in the ground.
Okay, sir.
Okay, there is a small announcement. Uh,